Hello. Today I'll be presenting our project titled COVID-19 Detection System with X-rays, powered by convolution neural networks. Despite the evolving nature of healthcare challenges, our innovative solution remains at the forefront of enhancing COVID-19 detection from X-ray images. Now let's dive into the details of the project. Now picture this, the urgency to advance the medical diagnostics in the field of global health crisis. That's the driving force behind our project. This isn't just about innovation. It's about offering healthcare professionals powerful new tools to enhance traditional diagnostic methods. In the field of medical imaging, CNN stands out as the forefront technology for detecting COVID-19 from X-ray images. Our project, driven by the robust framework of Keras TensorFlow, places a strong emphasis on accuracy to facilitate early detection and optimal resource allocation. Using CNN's innate ability for automated featuring learning and scalability, we pave the way for precise diagnosis and proactive public health measures. Our dataset comprises chest X-ray images, categorized into normal and mnemonic classes, totaling about 6K images sourced from Kaggle. Each image is standardized to the size of 224 cross 224 pixels. These images serve as the basis for training and evaluating our CNN model for COVID-19 detection. So these are the X-ray images of the normal and mnemonic cases. Now, this is a process workflow, and it outlines the steps involved in building and evaluating a CNN model for image classification tasks. First is the initialization process. We set up the modeling environment and initial parameters. Then we have pre-processing, where we prepare images through resizing, normalization, and augmentation. Then we have model architecture, which has about 3 layers: the convolutional layers, pooling layers, and dense layers. The convolutional layers are responsible for extracting features from the input images. Following convolution, pooling layers are used to reduce the spatial dimensions of the feature maps, which helps to decrease the computational load and control overfitting. After the features have been extracted and downsampled, dense layers are used for the final classification. Teach the model to classify the images by adjusting the weights to minimize errors. That is exactly what training does. And in validation, we test the model against unseen data to ensure it generalizes well. Finally, we have performance evaluation and the end result, where we finalize the model's outcome for deployment or further refinement. Now, this table outlines the output shape for each layer in the CNN architecture. Each layer's output shape is expressed in terms of batch size, height, width, and channels. Now, we can see that in the convolution 2D layer, it applies convolutional filters to extract features from the input data, while pooling max 2D layers reduce spatial dimensions by retaining the maximum values. The dropout layers mitigate overfitting by randomly dropping input units during the training, and flattened layers reshape the data into a one-dimensional array. Dense layers perform matrix multiplication and apply activational functions for classification. These layers collectively enable CNN to learn hierarchical representation and make accurate predictions. Our CNN model, specialized for X-ray image analysis, uses the capabilities of Keras and TensorFlow, providing both flexibility and computational power. Now, the primary metric for evaluating our model's performance is accuracy, which measures its effectiveness in identifying COVID-19 cases from the X-ray images. So this is the loss graph for testing and validating the dataset. There are a lot of fluctuations because we have used a relatively smaller dataset, which comprises of more COVID positive X-ray images than the negative ones. We are working on getting a larger dataset for effectively training the model. With an impressive accuracy of 80%, our model significantly surpasses random guessing, which will yield only 50% accuracy. Now, this is the accuracy graph for training and validating the dataset. We have a 2x2 confusion matrix here. Since we have only two categories, normal and mnemonic, we have more COVID positive X-ray images. And as a result, there are more false negative cases, but we're working on improving the dataset. Our project demonstrates CNN efficacy in COVID-19 detection, achieving about 80% accuracy. Future efforts include refining the model through techniques like transfer learning, ensemble methods, data augmentation, and weight adjustments. I hope you found this informative and interesting. Thank you. And these are our references.